Hello, so today, as you can see by the title, we'll be talking all about oscillations. So first, just to define what is an oscillation, in case you don't know, an oscillation is basically just a repeating of motion. For example, swinging, like a pendulum swinging. And in oscillations, there's something called a simple harmonic motion, which is also called SHM for short. And this is basically a repeating motion that is about a central point or about an equilibrium position. So another way to define this is simple harmonic motion is an oscillation caused by a force that repeatedly acts to restore a moving object to its equilibrium or central position. So by a restoring force. So basically, a simple harmonic motion is kind of by the title, a simplest oscillation. So it's an oscillation that there's a force that constantly wants to restore an object to its original position, which is its equilibrium position, and it repeatedly acts that way. So if you think about a pendulum swinging, you have a pendulum, and this is its original position, and then it goes from here to here, and then back, and then back. And all this is doing is this force that gets it to go here or gets it to go here. These forces are restoring forces, and they want it to be in this equilibrium position that it's at the beginning of all of this. And this relates to waves because what causes a wave is something going under oscillating motion, as you have seen in the pendulum example. So there is an equation for simple harmonic motion in which the acceleration of whatever is under the simple harmonic motion, whatever is oscillating, the acceleration is equal to the negative little omega squared x. And to define the terms, a is equal to acceleration. This little omega, this is given by 2 pi frequency. So F is equal to frequency. Then we have x, which is the displacement from the equilibrium position. So basically what we know is that the acceleration is equal to the negative square of the 2 pi frequency of the oscillation times the displacement of the object from its equilibrium position. And if you look at the signs, how this one is negative, you will always realize that the acceleration is negative. And that makes sense because the acceleration is always opposing the force in which the pendulum or whatever object you have is swinging. So to go with the example of the pendulum, we can have a pendulum here, that's our original one, and then as it goes over here, it slows down, right? This is at its slowest. If this is its peak, its velocity is at its slowest. Here, its velocity is at its highest. So when we go here, the acceleration is acting against us. So if the acceleration is the yellow force, the acceleration acts against this motion because, as you can tell, the restorative force is getting it to go over here. And it will make sense for this to slow down as it gets even more displaced from the equilibrium position. So here, where there's right here, this is at its fastest, and here it's at its slowest, and acceleration always acts against the direction in which the displacement is going. So in the end, whatever object you have that is oscillating, it slows down as it has a greater displacement. So we can also graph the movement of an oscillator, and an oscillator is anything that is oscillating, and you can graph the displacement from its origin against time. And you're going to get a graph that's going to look something like this. So if you take a look at this graph, you can see that x, which is the displacement, once again, this is the origin and this is the time. And what this graph is, what the equation for this graph is that x, so the displacement is equal to a, some constant, times the cosine of little omega times t. And once again, little omega is equal to 2 pi times the frequency of the oscillation. And this is a graphing from Desmos, which we will take a look at in a second a bit more closely. And in this case, t is time. So what we can see over here is that A over here is the maximum amplitude. So that means that we start this graph, t equals 0, that means we're the farthest away from the equilibrium point as we can get, right? So we start off by being at our maximum amplitude. So what you can see based on this graph is that you start off at your maximum amplitude, and you don't have to. You can use a sine graph and start off at the equilibrium position, or you can just move this graph. It depends, whatever you want to do. And you go down, 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 you reach your equilibrium position, you go to the opposite maximum, so you go to this side now, then you reach the maximum amplitude there, then you go back to your equilibrium position, you reach that maximum amplitude again, then you go back down, and you continue going to the other side like that. Makes sense, right? So here we have this graph again, and what you have to be careful of is that because this is Desmos, y is actually our x, is displacement, and x over here is going to be t. So what we can see is, for example, if we want to move our maximum amplitude to, let's say 3.4, this is what our graph would look like now. We would be moving like this. We would be having greater oscillations. Then if we wanted our little omega to be greater, then we're really, you can tell we're really raising the frequency. We have more oscillations for less time. And then if we, on the opposite, if we slow it down, if we have, sorry, I went a bit too far, 0.7, we have less oscillations for less time. And if we have a lower maximum amplitude, our oscillations are also, they're less, you can say, intense. There's less displacement from them. So the maximum displacement is lower, if that makes sense. I hope this helped you contextualize that graph. And the last thing that I wanted to mention is, based on this, the fact that x is equal to a cosine the omega t, you can use calculus, so just basically derivatives, to find out the velocity and the acceleration. So you know how the slope of the displacement is the velocity and the slope of the velocity is acceleration. So basically, put into calculus terms, the first derivative of x in terms of t is going to give you velocity is going to end up being negative little omega times a times the sine of little omega t. And then what we also know is that if you take the derivative of velocity, so this right here, you get the acceleration. But this also is just the same thing as taking the second derivative of the displacement. So you have the second derivative of displacement, and that's going to equal to the acceleration, which is going to equal to negative little omega squared a times cosine little omega t. So I hope that makes sense. And this is not really crucial. The main part is understanding how this works and why this equation works, and generally what oscillations are and what they are caused by. So I hope you are more familiar with oscillations and how they then connect to waves, and see you next week.